Today we're going to be working with both parts of the fundamental theorem of calculus. We're going to start by looking at some applications of part 1 and then introduce part 2 of the theorem. So our first learning target is to apply the fundamental theorem of calculus part 1 to find unknown values. In our last lesson we learned that if we were to take the integral of a function, we can evaluate it by finding the antiderivative of that function and substituting in our upper limit and then substituting in our lower limit. So this is the formula for the first part of the fundamental theorem, and we can actually use that formula as an application to find an unknown value. So we will be given one of the values, either f of b or f of a, and we'll use that process of evaluating the antiderivative and then solving this equation to find the value that we don't know. As we start the first example, you'll see that I've set it up following the format of the fundamental theorem formula. I have put the f prime function in for the integrand, and then I set it up equal to f of a value minus f of a value. You'll notice that we're asked to find f of 2, but that we're given f of 0. So that 2 and my 0 are going to be the values in my limits. And to decide between the two, I just choose the smaller value for my lower limit and the larger value for my upper limit. So if 0 is my A, gets plugged in there, and 2 is my B, because I always need to subtract f of B minus f of A. So once you've set up the formula, there's going to be different things happening on the two sides of the equation. On the right side, you're able to plug in the value that was given. F of 0 is replaced by the 4. And on the left side, I'm going to have to go through the process of evaluating that integral by finding the antiderivative of x plus 3 and then plugging in my limits, so f of 2 minus f of 0. Applying the power rule to the x plus 3 would give me x squared over 2 plus 3x for my antiderivative. And then of course I have to plug in my upper limit first. If you do 2 squared over 2 plus 3 times 2, that should give you an 8. And then when I plug in the 0, I get an evaluation of 0. And your expression on the right side just stays there. So 8 minus 0 is 8. And then to finish it out, I would add the 4 to both sides. So final answer for f of 2 would be 12. We'll save this second example, which is really similar to doing class, but if you feel comfortable, I just want to point out the notation looks different, but just keep in mind that dy dx is the same thing as f prime. They both are derivative notations. And you'll see this says y of 1, which again is the same as an f function, so f of negative 1. So give that a try if you feel comfortable. You can check the written key that's posted. If not, we'll do it together in class. So in the first example, we used an antiderivative to evaluate the fundamental theorem because we were given a function. But in this next section, we're going to use area to evaluate the fundamental theorem because we are given graphs. So let's take a look at that. When a question like this shows up on the AP exam, a lot of times they ask you to find two different function values and they give you one function value. Please know that you can't find two unknowns at the same time, so it becomes two separate problems. So you can only find one unknown each time that you're given one given value. We're going to use the same formula format that we did in the first example. So we've got the integral of f prime, which is what we're given a graph of, equals f of b minus f of a. And using the given x value and the x value that I'm asked about, I made the decision that 2 would be my lower limit and 6 would be the greater value of the upper limit. And so f of b minus f of a. We can start by substituting in f of 2 is equal to 4. And on this left side, as soon as I see the integral of a f prime, which I have a graph for, I'm thinking area. So I need to find the area from 2 to 6. And right away I notice I have a half circle, but it's also underneath the x-axis. So I have to remember that it's a negative area value. And we've got a half circle and the radius is 2. So when you calculate that area, it's going to be negative 2 pi equals f of 6 minus 4. And to finish solving for f of 6, we're just going to add 4 to both sides. So for the next value that we're trying to find, we use the same setup again. I noticed that the -3 would be the smaller of the two x values, so it became my lower limit, 2 is my upper limit. In my next step, I would plug in the 4 for f of 2. It happens to be the first of the function values, but that doesn't make it much harder to solve at the end. I noticed that I'm finding area from -3 to 2, and I found two triangles above the x-axis, so they're both positive. So using the dimensions I found, we've got an area total of 5. And so I would subtract the 4, and I would still have that negative f of -3, so I would just have to remember to divide through by a negative to get a final answer of -1 for f of -3. We're going to end up using these two values that we just found to help us answer this last question in this section. So they're asking us to find the absolute minimum of the function f on a closed interval from -3 to 6. So when I start thinking about that, I want to set up my sign chart of f to f prime, including my endpoints, and I need to decide where critical points are going to occur between that interval. Knowing that I'm looking at the f prime graph, I need the signs of positive and negative here, and I need to figure out where they change. Starting at the -3, I see that f prime is above the x-axis, so that gives me positive. It does touch down at -2, so that'll be a critical value, but then it goes directly above again, all the way to +2, so that's our next critical value, and the rest of the graph is below the x-axis. So then looking at the behavior of the f graph based on those signs, it looks like I have two possible minimums, one maximum, and then there's no change in sign here, so there would be a horizontal tangent at -2. So I have to decide between my minimums which one is the absolute, and the only way to do that is to look at the actual function values or the y values. So we'll set up a simple x and y equals f of x chart. We'll include our endpoints and our critical points. And luckily, we've already done the hard work to go ahead and fill in these y values. So for instance, we found that f of -3 was -1. We found that f of 6 is -2 pi plus 4. And we were given the value of f of 2 is equal to 4. The only value that we didn't find was that -2. It is 0, and you could find it by setting up that same formula, but to save time for the video, I'll just give you that value of 0. But we already knew that the minimum would occur at one of the endpoints. So comparing -1 to -2 pi plus 4, knowing pi is approximately 3, that would give us -6 approximately plus 4. This is the smaller value. So that would be our absolute max. All right, sorry, I think I just said absolute max, so let me say it correctly for our final answer. The absolute min is -2 pi plus 4 at x equals 6. And remember that our x and y chart serves as our justification for absolute min and max. This next whole box of questions is very similar to the one we just finished, so if you'd like to try that, great, go ahead and do so. If not, we'll save that for class. So I'd like to end by looking at a calculator application of the fundamental theorem. In this example, we're looking at the temperature of a cookie that is initially 96 degrees Celsius, but it's changing over time at this rate given by C of t, and we're asked to find the temperature at 3 minutes. So we're given a value and we're asked to find a value, and we're also given a rate. So I know that if I integrate a rate, I can find the temperature based on the fundamental theorem part 1 formula. So we can plug in the temperature we know, which is 96 at time 0, and then to evaluate, since we have use of a calculator, we'll use our math 9 to integrate from 0 to 3, that C of t function. So after plugging in your limits and your function, you should evaluate to get -0.886. Then by adding 96 to both sides, we get a final answer, C of 3 equals 95.114 degrees Celsius. You're welcome to try the last example on your own and check it with the key, or we'll save that for class. And there will be a short video introducing Fundamental Theorem Part 2 on the back of the notes.